Section 3C from the back of the book, dealing with uncertainty. In this section we're going to look at the topic of significant digits, and those are the digits in a number that represent actual measurements and therefore have meaning, and they are called significant digits. So we have a table here that gives a summary of whether or not a digit is considered significant. So I'm going to go ahead and run through that list of rules with you, and then I'll show you some examples to see how those apply. First of all, non-zero digits are always significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9, those are always considered significant when you see those in a number. If it's a zero, that's where it starts to get a little tricky, and we have 4 different scenarios to run through with the zeros. The first one is that zeros that follow a digit and lie to the right of the decimal point are always significant. So if you have a decimal and then there's zeros at the end, you would count them. So this is 1, 2, 3 significant digits, and again 1, 2, 3 significant digits, so those zeros do count as significant. Zeros that are between non-zero digits always count as well. So in 4002 you would count 1, 2, 3, 4 digits. In 3.06 you would count 1, 2, 3 digits. And also, if you have another significant digit because it's past the decimal, you would count the zero in between as well. So 1, 2, 3 there as well. So there are some cases though where the zeros don't count, and one of those would be if it's to the left of non-zero digits, and that tends to happen in these small decimal numbers. So if you have 0.006, if you just count the digits you see, it would be 4, but the zeros in the front don't count, so that's just one significant digit. This may look like 1, 2, 3, 4, 5, 6, but it's actually just 1, 2. We never count those zeros at the beginning of a small decimal number as significant. And then finally, zeros to the right of the last non-zero digit but before the decimal point are also not significant unless it's specifically stated that they are. So this might look like 5 digits, but we would assume this has been rounded to 40,000 and only counted as 1, just the 4, not the zeros. 210, we'd make the assumption it had been rounded to the nearest 10 and just count 2 digits rather than 3. So let's go ahead and look at that for some examples down here and try to determine how many significant digits we feel like these have. And then we'll run back and they're going to ask us about precision as well, so we'll do that also. So for each of the following, state the number of significant digits and then the implied precision of the measurement as well. So starting off with the significant digits, or also called significant figures, here we have zeros, and those are always the ones we're wondering about. They're in between other non-zero digits, so they definitely count. So 1, 2, 3, 4, 5 digits. So 5 significant digits or 5 significant figures. And then here, again, always focusing on the zeros. These are zeros at the beginning of a small decimal number, and we mentioned up above those do not count. So those zeros don't count, only the 1. So this would just be 1 significant digit in this one. 450,000 years, the zeros here at the end of a big number do not count, and we would assume that this had been rounded to the nearest 10,000 years, and so we would only count the 4 and the 5 as significant, and so that would be 2 significant digits there. And then moving down here, we have some zeros that count and some that don't. Zeros at the beginning of a small decimal number do not count as significant, but a zero in between non-zero digits do. So we have 1, 2, 3 digits that would be considered significant in that spot. And then finally, the last one is actually very much like part B. We have a bunch of zeros at the beginning and zeros in the front do not count. So we only have the 1 that counts there, so just 1 significant digit on that one as well. So those are all the different kind of cases that we talked about up above for significant digits, but this problem also asks us to talk about the implied precision, so I'm going to do that too. When you're thinking about the implied precision, you're just going to put the place value of the last significant digit. So the last significant digit here was the 1, and that was in the tenths, hundredths, thousandths place. So the precision would be the thousandths place. Going down to this one, the only significant digit was that 1. It's in the second decimal place, and that would be tenths and then hundredths. So the implied precision there is the hundredths place. Here we only had two significant digits, and the last one was the 5, and when we talked about that I said we would assume this had been rounded to the nearest 10,000, and that's because the place values are ones, tens, hundreds, thousands, and then 10,000s. So the implied precision there is 10,000 or 10,000. You have the 10,000s place. There we go. And then continuing on, three significant digits. The last one is the 3. We'll have to really count that one out because it's way out there. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So this would be considered precise to the millionths place. When you have those decimals, make sure you're getting that TH in there. And then finally, on this one, this was the only significant digit in tenths, hundredths, thousandths, 10,000ths, 100,000ths. So we would consider this was precise to the nearest hundredth, or sorry about that, 100,000th. So the 100,000ths place. Sorry about that there, got my TH a little too soon. Alright, so significant digits are about how many digits do you count as accurate, and the precision is about what place value did the last significant digit hold. Continuing on in section 3C from the back of the book, now we're going to look at what happens when you have significant figures that you've paid attention to and the precision of measurements that you paid attention to, and you start combining numbers through addition, subtraction, multiplication, division. We want to think about how the rounding that has occurred on your initial numbers affects what you would write down and how you would round the answer to these operations. So the rounding rule for addition or subtraction states that you round your answer to the same precision as the least precise number in the problem. Remember, precision is about place value, so it's saying that when you're adding or subtracting numbers, it's the place value that's important. And then the rounding rule for multiplication or division states that you should round your answer to the same number of significant digits as the measurement with the fewest significant digits. So when you're multiplying or dividing, instead of paying attention to the place value, you think more about the number of significant digits, and that's what affects your answers. And the note here is to avoid errors, you should do the rounding only after completing all the operations, not during intermediate steps. As I've mentioned several times, whenever you round, you bring in error, so we don't want to round every step of the way and bring in error at multiple points. We want to make our calculation using our numbers, just write all the decimals and digits along the way, and then when we get done, we would round it to the number of place values and significant digits that make sense according to these rules. So let's go ahead and take a look at that with a few examples. Alright, so for each of the following, use the appropriate rounding rules to do the calculations indicated above. So multiply 43 miles per hour by 25.3 hours. They don't actually say why we were doing that, but that would be a rate and a time. So it looks to me like we're calculating a distance here. So how far did we drive? So we take the rate, which is 43 miles per hour. And we don't need to do this, but I'm just going to show you the units on that. So we have the miles and the hours. And then multiply that by 25.3 hours. And I just wanted you to see here that the hours cancel out and we get a distance. But this problem is mainly about the rounding. So let's do the math. 43 times 25.3 comes out to 1087.9. And then the question that we'd have is that how we should write it, or should we round it? And this would be miles, by the way. And according to these rules, we should round it. And so then what would we round it to? Well, we're doing a multiplication. So the rounding rule for multiplication states that you should go with the fewest number of significant digits that you had in either of your two factors. This factor had 2 digits, this one had 3. So our answer should just be rounded to 2. So I would say this is approximately, and then if we're going to go 2 digits, it'd be 1 and 2, and so that's going to be the last significant digit I would write. Doesn't mean we just write an 11 and stop. It means we round it to that place, which would be the hundreds place. So we'd say it's approximately 1,100 miles. And it may seem a little strange, just throw those other digits away, but what you have to keep in mind is they probably weren't correct anyways. When we say we were going 43 miles per hour, that was just our best guess when we looked at the speedometer. We might have actually been going 42.73 miles an hour or 43.162 miles per hour. And if we knew that exact value and multiplied by that, we would have gotten different digits here. So we're just saying, look, if you've rounded this to 2 digits, you probably can't trust 2 digits later, because to trust all these other digits assumes this was 43.0000 miles per hour, and instead of being rounded to the nearest mile per hour. So we just want to kind of admit that this has some rounding in it and therefore can't be totally trusted, and then round our end answer accordingly. Let's go ahead and look at that with another example. A movie makes $73 million in revenue during its first week and then makes another $48.3 million the next week. What is the total revenue during the first 2 weeks? So when I hear them ask for the total, that sounds like it would be an addition. So I would do 73 plus 48.3. I would add those together. I'm just going to do that on a calculator off to the side. And I get 121.3. And then that would be million. And it doesn't really say, but it's probably $1 million if it's a US movie. And we'd be tempted to just leave it there, but if you look back up at the addition rule for numbers, it says you should round your answers to the same precision as the least precise number. So it's not about digits anymore, it's about place value. And this one went to the nearest ones place, this one went to the tenths. So the least of those was this one to the ones, so I would round that off to the ones here as well, and say that's approximately 121 million. And again, the idea is that both of these were probably rounded. This week they rounded it to the nearest million, the next week they went to the nearest tenth of a million, so this might have been 73.4 million or 72.6 or something like that. Alright, let's move on to one final example on this page. At the hardware store, you buy 25 kilogram bag of sand, and you also buy a 1.75 kilogram bag of nails. What is the total weight of your purchase? So again, we see total, so we'd want to add there. So we have the 25 plus the 1.75. Add those together, we get 26.75 kilograms. However, these were both probably rounded, this one to the nearest pound, this one to the nearest hundredth of a pound. And since this one was rounded to the nearest pound, that's the one that had the least precision, and that's how much precision we should put on our answer. We should admit that this probably isn't exactly 0.75 because that probably wasn't exactly 0.00. So we would just round that off and say it was about 27 kilograms. Okay. Previously in section 3A, we looked at the concept of absolute change and relative change, and in this section we're going to look at something very similar called absolute error and relative error. So let's go ahead and look at it with an example. We'll define it and then look at another follow-up example. So a package of hamburger meat is labeled as weighing 2.37 pounds, but the true weight is only 2.29 pounds. Find the absolute error. So just like we had the absolute change before, which was just taking the difference, the absolute error is also just taking the difference. And if we look at the definition box down here, when we do absolute error, we always do the measured value minus the true value. So when I go and look at what they gave me here, it says it's labeled as weighing 2.37, so that sounds like the measured value. And then it says the true weight right there. So the true weight is 2.29 pounds, that would be the true value. So when we do that absolute error, we want to take the measured value, 2.37 pounds, and subtract the true value, 2.29 pounds, and the difference, which looks like 0.08 pounds, would be the absolute error. So they were off by 0.08 pounds when they labeled this package of hamburger meat. When we go to look at the relative error, that takes into account how big this error is compared to the target they were shooting for. And we do that by division just like we were doing before. So if you look down here at our definition of relative error, you take the absolute error, which would be our 0.08 pounds in this hamburger package example, divide it by the true value, which would be that 2.29, and that will give you your relative error. And we would typically interpret that as a percentage like we did with the relative change. So find the relative error. I would take that difference, which is 0.08, and divide it by the true value, which is 2.29. And that's where you have to be careful, is making sure you divide by the true value. If you divide by this one, you'll get a different answer, and it's only considered correct if you divide by the true value. So just doing that on the calculator real quick. I have 0.08 divided by 2.29. I'm going to write that out with 4 decimal places, so approximately 0.0349. And then you could say that that's the relative error right there, but typically we would interpret that as a percentage, so I'm going to move that decimal 2 spots to the right and say that our relative error there was 3.49%. So there's 2 ways you could express the error that went into the filling and labeling of this package of hamburger meat. They labeled it as 2.37 pounds, and the truth was 2.29 pounds, so you could say they missed by 0.08 pounds or that they missed by 3.49%. And they're both just different ways of expressing that error. Same idea, but just is it measured in pounds or in the percent of the error. So let's take those same definitions right there and just apply that one more time. And this time we're going to apply it to a voting situation. So the vote count in a precinct is 2,563. It's later discovered that 5 votes were double counted. So find the absolute error. So first of all, we have the measured value. They went out and they counted the votes, and they found, or they counted it anyways, as 2563, just kind of like the label on the hamburger package. But it says 5 voters were double counted. So that means that when we go to get the true value, we would take that 2563 and we would have to subtract 5, and what would that give us? 2558. So if 5 votes were double counted, this is how many people really voted, but because 5 extra votes were counted, they measured it as 2563. So the absolute error is just that difference, and it would be measured minus the truth. And of course that just gives us the error they were talking about right there, which is 5 votes. And then if you want to say, well, what was the relative error? How bad is it to miss by 5 votes? Then you would take that 5, you would divide it by the true value, 2558 right there. Get a decimal for that. So 5 over 2558. Round it to 4 decimal places like before is 0.00. It's a 19, but it's a 5, so if I'm going to go to 4 decimals, I'd round that up to a 20. And then I'd move my decimal over 2 spots and say that's 0.20%. So they missed by 5 votes, which sounds pretty terrible, right? We're counting votes we shouldn't have. But that was just a fraction of a percent of error in the overall 0.20%. And well, again, that's not supposed to happen. Overall, when you see this, that it's about a 1/5 of 1%, you can see that it's kind of a small factor. And I think that counting of votes is more important than the labeling of a hamburger meat package, but the error here was technically worse because they missed by 3.49%. When they counted the votes here, they missed by a much smaller percentage. Though I would probably be a little less upset when my hamburger is mismeasured than when the election count was off.